This video is about transforming functions in terms of looking at a function and turning it into a graph, determining how each individual point is moved, and then given a chart with an original function and transformed points on the function, determining what the actual equation for the function would be. So if I take a look at this function up here, there are two things that are occurring. First, we have x values having something happen to them, and also we have y values having something happen to them. The y values are probably easier to figure out. So each of these y values is going to be multiplied by 3, and then we're going to subtract 7 from each of the y values. So if I take a look at some of the points that I know for sure are on this function, if I look at the y values, for example, 1 times 3 is 3, and then when you subtract 7, you get -4. 0 times 3 remains 0, and then when you subtract 7, you get -7. 1 times 3 is 3, subtract 7, you get -4. These 3 points, these 3 y values are going to be the mirror or the matching values that go along with the y values from these original points. Now, if you take a look at the x values, we can organize this in a couple ways. We can look at it the way the problem originally is written, like 3 absolute value of 1/4 x plus 2. Or we can factor out the 1/4 and see x plus 8 times 1/4 on the inside. And so I can organize this in two different ways. The first way would be the original problem. So I would subtract 2 and multiply by 4. Remember that everything is kind of opposite when we're looking at the interior of a function when it comes to x. So we would be basically solving for x on the inside. So if I'm solving for where the original is 0, I would subtract 2 first, and then I would multiply by 4, which is multiplying by the reciprocal of that. Or I could do it with the distributive property. So if I had 1/4 x plus 8, and I was solving that to see when that equals 0 or equals any other number, what I would do is multiply by 4 first and then subtract 8. So I could multiply by 4 first and subtract 8. So in either way, I would end up getting the same thing for each of these points. The red way first, -1 minus 2 is -3 times 4 gives me -12. If I did this with the black way, -1 times 4 is -4, minus 8 also gives me -12. So in either case, I would end up getting the same result. 0 minus 2 is -2 times 4 gives me -8, or I could have done 0 times 4, which is 0, minus 8 also gives me -8. And likewise, when I do the work here, I get -4. So when I graph this, I have -12, -4 as a point, -8, -7, and -4, -4. I have this absolute value graph that shows up down here, which if I graphed this sort of thing, I would see a vertex at -8, -7, and my slope, so to speak. And it would be very tempting to just think that we were able to go like a typical slope situation where we go up 3/4 in order to get to our next point. So in this case, that would be -4, -4. And in this case, that works very well. But that's not necessarily true if we saw it in another light. So these two equations have the exact same visual graph as our previous problem. So if we look at f of x, visually, this graph would look exactly the same. But the way that we get there is very different. So in this graph, what's happening is, yes, we have shifting. We're moving left 8 and down 7 and all this other stuff. But what's happening is that each of our original x and y values is getting moved in a different way. So each of our original points is getting shifted in a different way. In this problem, our y values are all shrinking. They're all moving down in some sort of way by getting multiplied by 3/4. In this problem, each of our x values is getting stretched in some way because we're multiplying each of our x's by 4/3. In our original problem, what was happening was our y's were getting stretched and our x's were getting stretched. And so the way that these things end up happening is different based on where things are. So that's kind of important for us to understand. We're actually looking at how the points are being transformed, not just what the end of the graph looks like. Okay, now in this question, we have a square root function, and we're given the original major important points and then what they look like after they're transformed. So what we're going to do is we're going to take a look at how the x's and y's are moved, and then we will go from there. So what I'm going to do is I'm going to kind of look at what we multiply by first and then what we add, and then we will write the equation. But first it may help us to graph. So -2, 3 is going to be a point, and that represents the initial starting point. So if I'm looking at this, if I have a square root function, I know that I'm going to have x plus 2 and then a plus 3. Because no matter what you multiply by, when you multiply by 0, nothing moves. So I can have 27 or 8 or whatever out here, but that times 0 is not going to move. And so then I would just add 3 to get the y value. So I know that my y value is going to be a plus 3 and my x value is going to be a minus 2. I know that's going to happen. So now what I want to do is I kind of want to see what's happening between these points. So for the y values, notice that it's moving up by 1/4 and then up by 1/2. So typically we were going up by 1 and up by 2. So from the first point to the second point is plus 1. From the first point to the next point down here is plus 2. Well, now it becomes plus 1/4 and plus 1/2. There is a common multiple that's occurring here. So in each of these cases, what I'm moving up by is multiplied by 1/4. So my y values are all getting multiplied by 1/4 first, and then I add 3. So multiply by 1/4, 1 times 1/4 is 1/4. Add 3, I get 13/4. And so on. Now for my x's, notice that for my x's, I add 1 and then I add 4. So plus 1 plus 4. Well, what ends up happening here? Instead of a plus 1, it looks like I am adding, this was -10/5, now it's -9/5. I'm adding 1/5. Instead of plus 4, this goes from -2 to -6/5. That's adding 4/5. So the common multiple here is 1/5. So if I'm multiplying by 1/5, that means that on the inside of the square root, I have to put a 5 times, because remember, when I'm doing the x's, it's basically the reciprocal of what ends up happening. So I multiply by 1/5, subtract 2. In this case, I have 5 times x plus 2. So I could also write this as 1/4 times 5x plus 10 on the inside of a radical plus 3. And if I look at this graph, -9/5, 13/4, that's not up by very much, but my square root graph is going to look something like that.